Oh, all right, guys, now it's for real. So today, I'm happy to present Jason, who will talk to you about the derivation of the Black-Scholes equation. Since Jason is a speaker, I will introduce him. Yeah, he's the organizer, right? So as per usual, when all right, so usually, okay, so in this seminar, it's mostly focused on geometric analysis and I mean just in general analysis. But today we're going to lean heavier onto just the pure analysis part. As many of you know that the Black-Scholes equation comes from stochastic calculus, and I know that most people in the audience here have never seen stochastic calculus, and that is like okay, we'll get through at least the important parts needed to give the presentation. So, a quick outline of the talk. So the first thing I'm going to start with is what I call something called the farmer's dilemma, in which we're kind of motivating the existence of such a question, or motivating the existence of the underlying question. And then after you have a little bit of motivation, what I'm going to do is give a heuristic idea of what Black and Scholes actually wrote down as a solution to this equation, this problem. And then we're going to derive it, right? Well, a brief introduction to a crash course in probability theory / stochastic calculus, since we're going to need it. Crash course. Stochastic calc. And then, doing the arrows, right? We'll do the derivation to get the PD. And then we'll immediately use the PD itself to write down a closed form solution to the equation. And if I have time, maybe I can say something about another type of option that comes up naturally in this situation. So let's start the talk, right? So what is the farmer's dilemma, right?
That's Jason.
Yeah.
Hold on, you mute yourself. All right, so farmer's dilemma. So here's where we're at, right? So we're a farmer. We are a farm together, right? So here is us represented by a single person with a pitchfork and a hat, right? And what do we do in our farm, right? We make corn. This is Indiana after all, right? So here's our plot of land and here's our corn. Not very detailed. You get the idea though. And we also have a tractor, right? And the tractor is how we're going to collect our corn. So what's the dilemma, right? So one year, you can only use a tractor so many times before it falls apart, right? Every year, your crops will give you new seeds to grow new crops, but in your tractor, you have to use every year, but eventually your tractor will fail, right? And so we're going to reach a point now where our tractor has only one more life cycle left, right? We have our crops, we have our tractor, we're going to gather up our crops, we're going to have to sell our crops, and then with that money, we're going to have to try and buy a new tractor, right? That's a problem that comes up. What's a possible risk in this hypothetical situation, right? Well, what if like the tractor prices go up, right? Like what if everyone's tractor starts breaking and all of them, everyone needs a new tractor? Well, then the price is going to skyrocket, right? Demand is going to, shoot up, supply is going to be relatively constant. So tractor price could go up. Ooh. All right. What is a solution to this problem, right? A solution is that we can buy what is called a call option. So we can buy a call option to, I want to say the word hedge, let's say to plan ahead, right? So I'll discuss in a second what a call option is more formally, but roughly speaking, we're like locking in a price ahead of time so that in the off chance that something bad does happen, we're protected. Right? So we're kind of securing how much we can pay for in the future. Now, if the crop amount doesn't, exceed the number we need, then like we're a failing farm. So we're going to assume that, we make enough money selling crops, right? So now we need to define some terms. Of course, the obvious one is, what is a call option, right? So an option more generally. So an option is a financial security, right, which is often thought as a contract, giving the right, but not obligation, to buy, which was called a call option, or sell, which is called a put option, at a fixed price, which I will call for the entire talk K. So K is the fixed price, it'll be completely constant throughout the talk. Or I say over a period of time. Over a period of time T. All right, so we have the definition of a put, the definition of a call, we have the definition of a strike price. All right, solid. So we're going to care about a specific type of option called a European option. So let's define that. So a Euro option, European option, is one that can only be executed at T equals big T, right? So at the very end of our period, right? We can decide if we want to use this, and if we use it, then we can pay K, sell K, depending on the orientation of the contract, right? So in the hypothetical situation we drew up, right, we want to call because we're going to buy a tractor in the future, right? So we're looking for that direction. Another thing you could do is an American option, right? So a European option is one that evaluates at the end of it. An American option is one that can be used any time between now and the big T. So time zero and time big T. The math of that gets a bit more complicated because things can happen between the two, right? So we're going to hold off on those today. All right, so what is the essential question then of the entire talk, right? We're the farmer, here's the tool, we need to buy one, right? So we're going to be given an initial asset price as 0. We're going to be given a strike price K. We're going to be given a big time T. I believe that's all I want, right? Solid. All right. Question, right? So given these variables, what is a fair price to pay for this? I'm going to call it a European call EC in parentheses. So I don't have to keep writing European call over and over again. So now the first thing that should jump out to you is, what is fair? Right? Fair for who? Fair for whom? Right? So the way that you want to think about fairness here is about arbitrage, right? So arbitrage is the ability to make riskless money, right? To have a fair means that both the buyer and seller cannot make riskless profit, right? So the way we want to think about this is, let's say P hat is the price that we derive from doing our process. If we assert a price greater than P hat, then the seller will have a unfair advantage, we'll put it like that, in order to make money. So this is unoptimal. And then if we're bigger than the price, then the farmer can actually gain a riskless profit by doing this, by building a portfolio, which we'll later see is a core idea. So this like middle of the ground price, so to say, this break-even price is what we're aiming for. So this is on the one board, okay. So now in order to start really getting your hands dirty when it comes to what Black-Scholes actually did, we need one more foundational definition, which I'm going to say in words for a little, and then I'll write something down, which is the first, if you ever take a course in financial math, the first concept they ever teach you based on the time value of money, right, is the notion of interest. So we need to assume the risk-free force of interest, I'll say in briefly what that means in a second, is constant. And we're going to denote it the symbol R, and R is going to be positive. Okay, so what do I mean by this? Well, I mean $1 invested at T equals 0 will turn into, and we've all seen this in our calculus classes, right? E to the RT at time T equals big T, right? That's what I mean by we have risk-free profit, right? You put your money in a bank, they pay you continuously compounding interest of R. And this is what it looks like. Another way to write this is that if we have a dollar at time big T, we can discount the dollar back to e to the minus RT at time 0. So R has like this valid definition in either direction you go. All right. So with that out of the way, we can write down a, let's say, heuristical theorem that Black-Scholes proved, right, in the 70s. So I'll write this in like air quotes, right? This was 73. All right, so if R, S0, K, and T are given as above, right? So interest rate, initial price, strike price, period of execution given as above. Now we need to make one assumption that is going to be the majority of why the talk is hard or easy, you know, is that the stock price or the asset price, we're going to call S of T, is a stochastic process modeled on, let's see how can I put this reporting problem. All right. Modeled on ds equals mu s dt plus sigma s dw. Right, so this is known as a stochastic differential equation, right? And we make one, I'm going to put this in parentheses here because it's like maybe not a, it's not such a mathy condition, so to say, but we need an ideal market, we need an idealized market to buy and sell things. So we have an idealized market looming in the background that we can buy and sell things from. All right. Then there exists a fair price for this guy that only depends on the initial data, right? So we don't actually need anything else to get a fair price. All right. So this is at least the groundbreaking work. This paper's got like 60,000 citations or something, so quite prominent. All right, so now the obvious questions, right? We see the equation, right? What does that symbol mean, right? I didn't tell you, right? You know, right as of this point. So let me at least say one thing of what this means, right? So I will define everything in more detail in a second, or throughout the talk, I should say. What I mean to write by this is more of a shortcut for this guy. So S of T is equal to S of S. Well, maybe that's not a good symbol. S of A, why not? Plus integral from A to T of mu S dt plus integral from A to T of sigma S dw. Right, so this is what this shorthand will end up meaning. So now, some natural questions that come just immediately looking at it, of course, is, you know, obviously what is W, right? So that's the first question. Right, another question is, you know, slash what is, you know, dW, right? How do you make sense of the integral itself, right? So what does it mean to write this collection of symbols down, right? So it's one thing to define W, it's another thing to define the integral on W. And then lastly, and this is more of another heuristical maybe point, is this a good model, right? So is this a reasonable model for price? Right, so these are all questions. There we go. All right. Let's make sure I'm on the right page for things.
But at least I think it's short. His farm is bankrupt. So
my farm is bankrupt.
No, he's the Black-Scholes, right? One of the guy owned a farm and bankrupt. His farm is already gone.
Damn.
That's what we're going to say. That's your third question.
I did not know that, but I'll take your word on it. So
is this mu a number or?
Yeah, so at least for now, that's a good question. So we're taking mu to be a positive number, constant, and sigma will also be a non-zero constant. Thank you. All right, so the first question we're going to address, of course, is W, which is, this is obviously going to be Brownian motion, as that's the essence of all of this you know, stochastic calculus stuff. So DW is kind of funny. So as itself, like sitting here, this has really no meaning. We don't think of the differentials themselves, ds, dt, and dw, of having any inherent meaning. What we think of them as, when you write it in this combination, we mean that you're a stochastic process. I'll say what that is later, with this form, right? So this is a shortcut for this. So dw we can kind of ignore, right? So what is w? Right, Brownian motion. And then the integral here is a stochastic integral. So we'll talk about how to build those, right? Or a slash Ito integral, sometimes called. There's other versions of stochastic integrals, but we're going to do Itos. And then, is this a reasonable model? And what I mean to ask by this is to say, okay, like, think of like, beginner logic, right? If a premise is false, then anything, false implies anything is true, right? So is this actually, do we have like effectively an existence and uniqueness theory for such results, right? That kind of ground us and say, okay, like such a requirement is reasonable and we can actually, do something positive with it. And that answer is yes, right? So there does exist some existence uniqueness theory for SDEs, right? I won't really have time to get through to this, but Brandon may be able to shed some light on it afterwards, or I can say something afterwards about it. All right. So now we have to kind of get into the weeds a little bit more. We have to define these objects. And this is where I'm going to take like a liberty in being the speaker and say that, like, I'm not going to discuss everything, most things at all even, and most things are not going to be in full detail. And, you're going to have to take some of the theorems on faith, right? And additionally, you're going to have a bit of a probability background already. Like, I'm going to take into the assumption that most people to some capacity have seen measure theory, have seen independence of at least events, central limit theorem, distributions, like some of these basic things that you'd pick up in a normal probability course. But I will like specifically highlight the ones that will need to be in this talk. All right, so if I say something that you don't understand, yeah, what's up?
So just to clarify, so S of T, that's the price of it. That's the option, that's the fair option price.
No, this is the stock price.
Oh, wait, okay, sorry.
Yes, I haven't written down to you what a formula would look
Oh,
like this for this yet.
Oh, I didn't see that. Okay, sorry. So,
Yeah, so I haven't, yeah, I'm concealing this for now.
okay, wait, so this is sorry,
Yeah, you're good.
can you explain a lot? So you're saying, you're asserting the stock price is this process,
Yes,
and then you're saying, in addition, there exists a fair.
yes. This is part of this. So this is part of the assumption. The only conclusion is that with these assumptions, you can actually derive a formula. I haven't written down at least in a formula yet to say that this is the cost function or this is the. I'll do that later.
So the S of T, does that depend on these option prices, or does that come into the existence of the fair price of the option?
Say it again.
So S of T,
Mhm.
does that depend on like K, or does K
No,
come into the fair price?
Fair price.
Gotcha.
Yes. So I'll say I'm going to define it very shortly. But the stochastic process also has another hidden variable, if you want to put it like that. So S of T for any fixed time is actually a function.
This is the random variable for each t.
I'm going to get to that in, like right now. Yeah. So definition, just so we're all clear, because most people again study measure theory and not, probability theory here. So given a probability space, right? What Brandon just said, X is a random variable. If X is just a measurable function, or all measurable, right? So I'm going to use the language, I'm going to try to say things are measurable functions, not random variables in this talk, because most people here study measure theory. But when you hear the word random variable, it just means a measurable function. All right. So I guess the other thing then is the other symbol that gets commonly thrown around is the expected value of a random variable is just the average against the probability measure. That's it.
The probability measure is like a measure that is total to 1, right?
Yes, yeah, the measure of the big space is equal to 1. Yep. Right, I can like implicitly put like a 1 over probability here to mean average, but it's equal to 1. All right. Questions so far? So definition, and this is really going to kick off. So a stochastic process X is a one parameter family of measurable functions. Measurable always mean Borel here. We're gonna talk about real valued things. You're always gonna have the Borel as the output. So we mean Borel. All right. So what do I mean by this, right? For every instance of time, you're gonna give me a measurable function. Okay. Not so bad. And if we fix a little omega inside a big omega, we're going to define the sample path to just be the function that takes t to this guy. I'll draw a picture in a second, but make sure we have all the definitions in front of us. Make sure online can see the definitions as well. All right. So this is it. So a stochastic process is just, you just take, there we go. Right, you just take your collection, you take a time indexed collection of random variables, measurable functions. And the a priori, and this will like be important later, we don't have necessarily any conditions on how they have to behave with each other. As time varies, it's just a literal indexing of functions. We will later need to put assumptions on them to make things kind of like work better. But a priori, there's not much happening. All right. So I'd like to give you an example of a stochastic process. And it's the famous one. I'll draw a picture actually first, right? So what do we have in our head? So how do I visualize or how do I think about a stochastic process? I'm going to imagine in my head stochastic processes have at least continuous sample paths to draw pictures, right? So fixing time, when we think of a random process, we often think of, you run the same experiment over and over and over again, and you get a different looking path every time, right? I'll do some colors. Right, so here's one, so function of time, and we plug in some random sample point from our guy. That's one sample path, and then we could have another guy, plug in a different sample point, right? So this is like the intuition I have in my head, right? For stochastic processes, I like to think of them as like, actually, I don't really think of the stochastic process themselves like as the one parameter family. I think of much more sample paths in my head when I write these things down.
That's because this definition is not really a definition. What's your point?
Oh, the real line. All right, so the canonical example that we're going to talk about today is Brownian motion. And by this, I mean continuous random walk on the real line, all right? So C0 random walk on. All right, so we have to construct this, right? So I have to build a stochastic process for you because as of right now, we just have the definition and we don't have anything else, right? So, I guess in theory, we could just write down like literally just whatever we felt like for measurable functions, just index them by time and call it a day. So a random walk, right? If I draw a line and I put a particle on the line, right? When I think of a random walk or random movement on a line, right, you kind of think of that the particle as time goes on kind of like drifts. So maybe this is like time equals 0. You start here and maybe it goes a little to the right and then maybe it goes a little to the left, and kind of bounces back and forth. And what you're realizing initially is what we want to say is, I'm going to redraw this picture, slight angle. So time equals 0, what can we think about? A little more space. I'm going to erase this one. So, all right.
I mean, that's a random walk already on the real line.
This one.
This is a picture of a random.
I know. I said intentionally I'm going to do it continuous so that I can look. The picture looks nice because I'm not going to draw something that isn't continuous, right? So we have t equals 0. At t equals 0, our particle, we know where it is, right? We're taking a particle, we're putting it at the origin, right? So in some sense, the distribution that the particle takes on is just the Dirac mass at 0, right? So here's the origin. Right, here's our time equals 0. But what happens as soon as we get the time equals 1? Right, well, let's look at our picture up here. Right, if you let the particle go for 1 second, I mean, you can do like an Einstein theory here. The thing can only travel at the speed of c. Can only travel at c, right? So you can't get that far away. But in spirit, right, your guy could like move a little bit, but it's kind of controlled, right? In fact, the probability of how far it can move away actually looks kind of normal. Right, so initially you're concentrated at the 1 point, but then where you could be at 1 second is kind of on a distribution. And at 2 seconds, the distribution gets wider, right? You give yourself more time to spread out. Okay, hopefully that looks a little bit wider. And you can repeat this process, right? You can just let time just go on as long as you want, and you'll get a wider and wider distribution of where you think the particle could be. All right, so T large. So what are we kind of observing, right? So we're saying that here, okay, like the distribution function, roughly speaking, is like the Dirac mass at 0, because we know, right, we're sticking the particle at the origin at time 0. And then at time 1, our particle is roughly speaking like a normal distribution centered at the origin of standard deviation 1, variance 1. And here we take a normal distribution centered at 0 and 2. And then notice as you go larger and larger and larger, it kind of behaves like a normal distribution with respect to the time variable. All right, so that's at least kind of how we think about the distributions themselves. The trick now is we want a stochastic process whose distributions at every time slice look like this, right? And that's how we think of a random walk then, right? As we're somehow like sampling some amount of this path. Right? Hopefully that makes some clarity. So with this picture in mind, the definition by Wiener tells us that a real valued stochastic process, and this one's going to be called big W, is called a Brownian motion if we're going to have 4 conditions. So the first one deals with the initial starting point, right? So our first function is 0 almost everywhere. Next one we want to do, that I wrote down at least, was that if you take 2 times, take 1 time bigger than another time, both of them possibly positive, we're going to assume that this increment is normally distributed with center 0 and variance T minus S. All right, notice here, quick remark, if S is equal to 0, right, we already said that W of 0 is 0 almost everywhere. So then W of T becomes normally distributed from 0 to n T, which is like what I wanted to do over here, right? So this kind of that picture is captured in here. And then we have an information argument, I'll call it like this. So for each 0 less than T1, less than T2, finite collection of times, we have that this all right, these guys are independent as random variables / measurable functions, right? Because remember, a stochastic process for every time you get a function, right? So these guys are all functions. We're saying that they're independent. And then fourth is we want continuous sample paths, right? For almost every omega and big omega, we want that T goes from W T omega to be continuous. All right. So this is the definition we're taking. You see? Now I'm kind of pulling the wool over your face a little bit, right? Because I wrote down this picture of a random, a random walk, more or less, and I said to you, oh, like this is the Brownian motion, and like then I wrote some definition down for you. Yeah, I've yet to actually show that such an entity even exists, right? So in some sense, I still haven't even given you your first example yet, right? But we're going to do that in a second. And so How do you go about constructing such a thing, right? So, so rather than giving a long description of how to construct such a process, I'm going to state a theorem due to Levy. Brandon, you have any idea when this was proven
I
actually?
actually proved this.
That's great. Do you know when this is proven?
That was my project.
Do you know when this was? Do you know when this was?
Of course,
Here.
the distribution, the Leibniz distribution of random walk, of course.
We're done with you. Let omega UP be our probability space, and we're going to take a sequence of IID 0, 1 distributed. It's a sequence. All right, again, identically distributed means that all of them have the same distribution function. They're independent from each other, so the information doesn't cause each other to make decisions more or less, and they're all 0, 1 distributed. All right, so this is an assumption. Assume we have such a collection. Then we have one-dimensional, then we can construct 1D. Brownian motion. All right, again, yeah, we can construct the Brownian motion as I wrote up there. All right, so how do we do this? Right, and this is going to be the fastest sketch of such a quantity because I don't want to spend too much time on some of the proofs here. So with these guys, we can write WT omega still. We can define it to be the sum from n equals 0 to infinity of AI. Oh, that's an I. So we have the random variables here, so we can plug in an omega, and then we're going to multiply by these special functions, which I'm going to draw a picture of in a second. So we just write down this, series. There's a lot of things you have to check, convergence, like what the hell are the SIs, et cetera, et cetera. But this will work, is the idea. So what does S1 look like? All the S's are more or less tent functions. So S0 is going to be defined to be just 1. All right. S1 as a picture is going to be the tent function from 0 to 1. S2, I'm going to give myself some space in a second, I will give myself some space right now. All right, S2 is going to be that guy. S3 is going to be that guy. S4 is going to be okay. Is that like a fourth to everyone else? You get the idea, right? So there's S5, 6, 7, and then you're just going to keep going forever, right? You're going to make them thinner, you're going to repeat, you're going to make them thinner, you're going to make them repeat, etc. This will form a orthonormal basis for L2 on 0 to 1. That's what we're trying to do here with that. All right, so you have these functions, we make this series, it actually ends up working, right? I don't want to say much more than this on the convergence and all of that, but Levy ultimately shows that if your probability space has such IID random variables, then you actually have a Brownian motion process, you can build one. So like as a heuristic assumption, or as an interesting assumption, I guess, does our universe actually have these things? Can we, build a Brownian motion in real life? I think this is like somewhat of a philosophical discussion. But like from this point forward, we're going to assume that our probability space just has them. So we can take the Brownian motion and do something with it.
The converge only L2 or is almost everywhere, the series.
Not error, it's in distribution.
Yeah.
Only in distribution.
Just picture, so.
You need a Kolmogorov theory, like to show such a thing actually converge almost surely.
Yes.
That's actually my dissertation.
I'm
This is-
avoiding the details. That's what we're trying to do here, right? All right. So yeah, what's up?
Picture. So the AI serve as a basis of the
No,
space,
sorry for which things?
L2 space. I think.
No, SI as well.
Okay.
Yes. Oh, I guess the one thing I didn't say. Thank you for fixing this. These guys are only for 0, 1. So we defined a Brownian motion process from 0 to 1, and then you just glue them together, right? So you have 1 for 0, 1, you restart 1 to 2, restart 2 to 3, et cetera, right? And that's how you get the entire line.
But AI looks like the basis on probability space. I mean, AI are all measurable function, right?
Yes.
Okay, let me think about it. Thank you.
All right.
If you have such a independent sequence to your simple space, like the domain, it's more or less like a infinite product kind of thing. So I don't think it's easy to.
Actually, even the definition of a stochastic process is really to the product space, to the T copy of a
Yeah.
line. So that's
Also the things I don't want to write down, but yes. All right, we're going to move on because we can get bogged down in the details of this stuff quite quickly. So the next thing, so we're going to say at this point that we have, a priori maybe a little bit Brownian motion locked down, right? We get the basis idea that this thing exists and there's some nice product properties about it, and the sample paths is what we think about, when we think of random walk. So the next thing is, how do we, I erased it now, but how do we define the stochastic integral? So that we can make sense. Remember, in the background, we have this, what I call it, a to t sigma s dw looming in the background there, right? So we have to make sense of what we're looking at now. All right, so to do this, I'm going to first stand with a point of motivation, right? And by motivating, I want to say, how do we want to think of integrating 0 to big T of, let's say, w itself against w? Right? Maybe, if we write down this, we'll have some better ideas of how to write down a different process. Because W, as of right now, we have some decent control, right? We've kind of built it. We know how the properties look. Maybe we can say something positive. So what the community has done is to say, okay, let's look at left Riemann sums, right? So we're going to define the left Riemann sum. This is the Riemann sum of the sum partition and some parameter that chooses the marked point or the sampled point from the interval. So we'll define this guy to be sum from what indexes I used before I mess things up. I used 0. So k equals 0 to m minus 1. But now we're going to take a point in the interval. I'll write that down in a second. To t k plus 1 minus w of tk, like this, such that p partitions 0t, and tau is given to be equal to 1 minus lambda plus lambda tk plus 1. All right, so we write down a right Riemann sum, or not right. We write down a Riemann sum that we think maybe could approximate it, right? We have this dw here. That's like kind of like this piece. You have this height piece, that's possible. And obviously we want to say, okay, maybe the limit of this sum, will be what we want. Right, so what happens is the mesh size go to 0. So to this extent, I want to also make one other quick observation, right? Because we want to say somehow that, we're hoping that this guy is equal to the limit as n goes to m, partition size goes to 0 of rp lambda. What's something kind of clever here, though, that's kind of lurking under the shadows, right? Well, for any fixed t, these things are all measurable functions, right? So this is a sum of measurable functions, which is itself a measurable function. And we're saying that we have a limit of measurable functions, which, accountable limit of measurable functions is measurable, right? So this thing will be a measurable function. Hence, at least, as right now, the integral itself is a measurable function. And this is actually not somewhat unbelievable, because w, remember, is like a 2-variable function, and we're only integrating t, right? So this thing is also a random variable, will ultimately also be a random variable. So the integral depends on the sample point you select, right? So it's a function, but, well, I'll talk about the intuition for what the symbols actually may mean after I write down some more things. All right, so as I notice, I'm trying to not be too late on time. So, lemma.
but it doesn't convert.
We're getting there. One thing at a time, Brandon, We have quadratic variation, right? So, not everything what I'm writing here for quadratic variation usually goes by this name, but that's okay. So we're going to get some intuitions about the sums and these behaviors, right? So let the closed interval AB be contained in 0 to infinity, right? And we're going to consider a sequence of partitions such that of AB, such that the mesh size goes to 0, right? Then the conclusion is as follows: that the sum from k equals 0 to m n minus 1, w t, oh, not w, sorry. It is w, but I want just the endpoints. Tk plus 1, w, tk minus 1. All right, we want to say that this guy would be converging to b minus a. And L2 of omega, right? Because now we're thinking of them again, they're functions, right? They're functions. But this isn't true. I'm surprised Brandon didn't yell at me immediately. So the point of quadratic variation is it's squared, right? That you don't actually get that these pieces work, but you get that their squared pieces actually work. And this actually is a heuristic for how we actually should think about maybe dw or an integral against dw as a whole, right? I'm going to throw one more thing in here that isn't usually called quadratic variation, but more easier for the talk, is that integral from 0 to t of w dw then is w squared t over t plus lambda minus 1/2 big T. And that's we'll get to that problem in a second, because you're integrating what looks like x dx, and you're getting x squared over 2 evaluated at t, the top bound. But then you have this other, random ass term lying in the background. So let's talk about both of these conclusions.
Wait, that term is not a random though.
But in what sense of the word random do you mean? Do you mean colloquial random?
No, I mean that's a deterministic, right?
Convert b minus a or b minus a squared.
B minus a, right? And intuitively, you might think it starts going to b minus a, but the square of it actually goes to b minus a instead, right? That's the unintuitive part, right? All right.
The right hand side have the lambda.
Yeah, you're right. This one does have lambda, true.
I mean, you're saying your integral depends on lambda.
Good. That's the second remark. So the first remark is what is the quadratic variation? The first implication tell us, right? It tells us that, okay, so as you send the partition mesh to 0, then you can kind of think of the sum as though you're converging on the integral a to b of dw, and in this case squared, right? This is again like a heuristic argument. Don't take this as face value, right? So this thing is roughly speaking, right, the limit of the sums of these change of deltas squared, as I have it written there, and we're telling that these things convert to b minus a, which is of course a to b dt. So just like kind of staring at a heuristic level, you might think, all right, well, dw is sort of like square root of dt, right? And you'll often see this get thrown around a lot in some of the probability books. It's like a first discussion of how you think about a stochastic integral, and this is like the reason of why it comes up. Now, Hung's question, right? We have this lambda looming around. Like somehow the integral you write down actually depends on which point you choose, right? You could choose the left endpoint, you could choose the right endpoint, you could choose the middle, you could choose anything you want, right? Lambda is a parameter. So what are the two natural choices, right? So the one natural choice is of course just 0, right? To make the choice easy, take the left endpoint. Another natural choice is of course a half, right? If you take lambda equals a half, you completely delete what looks like I don't want to call it a sickness that comes along with it, but you delete the other term sitting over there.
That's not an integral anymore.
I never claimed either one were at the point right now. However, Brandon is hinting at it that 0 will actually be the one we take.
Yeah.
Right? And this is the intuition that I think is supposed to be carried forward. Right? So on any given time slice, T1 to T2, right? You need to actually plug in tau, right, into a stochastic process. The problem is if you plug in a half, you somehow have to know the future information into the interval to evaluate it. And that is what makes the sum. Whereas if you take a left endpoint, you kind of have the information in front of you, right? You don't have to take I don't want to call it a guess, but you don't have to reach into the future, right? You can use the things that are presently known to you. That is why lambda is taken to be 0, which amounts again to a left Riemann sum. All right, and this is what ultimately will help define the Ito integral, right? Again, I'm not going to tell you where the computation comes from for that, but we can talk about formal computations later. All right, so now what we want to do for a general stochastic process. So this is our motivator, integrating w dw, and we said, okay, a left Riemann sum is going to be the method, right? So question now. What about general G stochastic process, right? Well, at this point, I would rather not talk about which things work. And instead, we're going to say that, when you want to define an integral on a class, you need to pick a suitable class of things that work. A priori, I told you that there was nothing special about a stochastic process in terms of how the layers of them interact with each other in the time sense. You will need to now make assumptions that they kind of glue together in like a reasonable way. This is often called progressively measurable. We're not going to talk about that, right? But there's a gluing procedure to make it kind of like the measurability, at least, of the gluing procedure work. And then additionally, I'm going to use symbols that are like intuitive to a measure theorist, but I'm not going to actually formally write down what they mean. So the suitable class is going to be this L2 of 0t type object. So you're thinking L2 in like normal sense. This is progressively measurable functions that are real stochastic processes such that some integral squared is finite. Right? So this is the class we want to do. And ultimately we're going to define is the following. So we're going to define the measure theory way, which is you define the integral, the Ito integral on step L2 processes. Right? So you define, just like how you do in the normal measure theory, right? You take your simple functions, you define the integral, and then you approximate. And we're going to do the same thing. So you define the integral in a step process. You show the step processes approximate the usual ones. And then you define the integral from 0 to t of any g in that space to just be the limit. In the L2 sense, limit. And Gn here is going to mean step. All right, that is where I want to draw the line on general stochastic calculus, drawing the line on creating the stochastic integral. All right, I'm still trying to power through some time. I don't think it'll take that long to actually do the derivation of the Black-Scholes equation, so it'll be okay.
Sorry, so that W is a Brownian function.
Yes.
You define the integral for all the process?
What?
You define an integral for all the process?
In what sense? You mean other process?
For some process, for example.
No, you cannot do that. This W must be Brownian motion.
Yes.
That's the
Are you
thing.
talking about?
No, I mean, is there other,
Yes, of course.
is there any other notion of integral against other process?
Yes, but we're not going to worry about that. We're going to stick to W. All right, we're going to hug W tight. All right, so the last thing we want to say is what is the intuition of this? And I'll just say it in words, right? So remember we thought of a stochastic process. We pick a sample point and then we have the path, right? In this sense, I want to also like pick a sample point. And once you pick a sample point, you kind of have a path for W, right? And this is kind of like a weighted sum along the stochastic path, so to say. And you're just summing up the different pieces of Brownian motion. All right, now what we need to head towards is Ito's lemma, right? Which is the main tool we need. The main tool we need to actually do the derivation of the Black-Scholes equation. So Ito's lemma is as follows. All right, so I'm going to do a little cheating here and say you can also define an L1 in like a very similar fashion, L1 and L2, just like you would kind of intuit in measure theory, right? So for F in L1, G in L2, and we take dx to be equal to F dt plus G dw, right? This is from the earlier, remember towards the beginning, I said that this collection of symbols is represented by, like these things, right? So just keep that in the back of the mind. All right. So these guys, now we assume that we have a function u that goes from r across 0t to r. And we want u partial derivative in the t direction, partial derivative in the x direction, and the double partial derivative in the x direction to all be continuous. Right? So we assert that we have such a function with all of these properties. Then we have the chain rule in stochastic land, right? Then let y of t define the process that is u of x of t comma t. right? So this is the chain rule S behavior. And we want to say that the stochastic differential of y has a nice formula, right? ut plus uxf plus 1/2 uxxg squared dt plus uxg dw. So
The Taylor theory.
yeah, pretty much, right? So the one thing I want to say about this real quick, of course, is that we're doing a one derivative and a second derivative shows up, right? This is like the fundamental thing that makes stochastic calculus a little bit different than your regular calculus, right? That you have the second derivative term popping out. Of course, you should expect it to be random, right? This thing is a random variable, y is a random variable, so you should expect a dw term. So this part, a-okay. This part, a-okay. This part, maybe a little bit weird. So now, with my remaining time, I'm probably gonna go a little bit over, but try not to go too much, is we're gonna now put all the finance together. And we're gonna reintroduce we have now Ito's lemma is effectively the tool that we need. We're gonna now use Ito's lemma to solve our problem.
So the farm bankrupt. Actually, the farm bankrupt in 1998, I think. Yeah, his farm.
Sure. All right, so that's done. Oh, the one comment I will say out loud is the existence uniqueness theory for the actual SDE theory is kind of like Picard-Lindau law. You do some, successive iteration of some form of an ODE and you make the estimates go to 0 and life becomes good. So such an entity exists, and you also need the coefficients to be like a Lipschitz type behavior, just like Picard-Lindau law. All right, so now we're going to return to, I called it Q star, right? Pricing of European coal. All right, so fair price. So let's talk about this real quick. So what I'm going to say here is going to have some more financial math terms listed to it. That's the present value of the expected payoff of owning the contract, right? And in symbols, this is going to be this fine collection of symbols, and I will not leave you hanging, and I will tell you where this comes from, right? So two things: why does this make sense, and why does that make sense, right? So the first guy, present value of expected payoff. So if the price is less than, if the future price is less than the strike price, we just don't use the contract, right? The thing you had was cheaper than, the price of the object is cheaper than the contract that you held. The contract is worthless. All right. If S of t is greater than k, then the payoff is S minus t, or S of t minus k, obviously, right? And so the general formula, of course, then is just taking the positive part of it. Okay, solid. Now this is the payoff. But remember, we have a stochastic process. So S is random. So we're going to average over all sample paths, right? So now we get the average payoff, right? And that's equal to this guy. All right, solid. And finally, but time value of money, things that we have to have in the future need to be discounted down to the current day. And the way you discount $1, remember, as I said before, $1 then becomes e to the minus RT dollars today. So you discount this whole thing down to today, right? So now discounted. And we get the formula up top. All right. So that's at least that connects the second equality. What about the first thing? Why is this a fair price? Well, remember how I said to you in the beginning of the talk, if we had such a fair price and you exceed this number, then the seller has arbitrage opportunity. And if you're less than this number, then the buyer has arbitrage opportunity. This is, air quotes, the number that will do it, right? So this is, as I wrote earlier, I think I called it P hat, right? This is our P hat. Maybe, right? It turns out it's actually not P hat, right? So problem, right? What is the problem? Well, I never told you what the expectation is taken with respect to, right? This is like real life now. And in real life, a measure that kind of exists philosophically is the world measure, or whatever people like to call it, the probability measure that exists in the universe, which is in some sense, what is the probability based on historical data? And this is not risk adjusted. So the world probability measure is not risk adjusted. And the rough answer is because of drift. Right? So because we have drift, there can be the better the price that you can attain on drift, the better the approximation you'll get, and you'll have a differing in price. This causes an arbitrage opportunity that creates unfairness. So this approach doesn't necessarily work, right? As it looks right now. So what Black and Scholes did, and this is the way that we are going to actually end up solving the problem, made the following key insight. So we're going to let C of t be the value of the contract, so the value of the European option, the European call, at time t, right? So this is going to be the value of it. All right. Observe, as we saw, that the value at big T is just S of t minus k plus. Again, because we're thinking fairness here. Fairness, right? No arbitrage. So, okay, so what happens when you do this? Well, what we want to do is price it. Price it as a current day problem. What I'm telling you is that we have a terminal condition. At the last point in time, we know it, we expect to know what it is. But what's the current number looking like, right? We want V of S0 at 0, right? This will be the fair price, right? This is our value of the option. What is it at time 0? That's what we're trying to solve. This is the PD problem that we're kind of setting up. Now, the insight, so maybe that isn't the key, but this is really the key. So you write down what the cost function or the value function looks like. If we can construct a portfolio only comprising the stock, I'll say it like this, a stock and risk-free asset, like a bond, that mirror C of t, then we have control, right? If we can build a portfolio, right? You have the cost function and you have your portfolio, and if they both evolve with the same dynamics and they end up at the same spot, then they must have started in the same spot, right? That's a uniqueness type statement in which we do have uniqueness of SDEs. So we're going to use uniqueness to say, okay, at a future time they agree, they follow the same dynamics, therefore they agree at the initial time. And the initial time, the initial value of the portfolio will be the fair price, right? So now let's write down the portfolio. All right, I will not go too much over, but this is the essence of the talk, more or less. So our portfolios can be weighted. Pi is the portfolio, the value of the portfolio T, by number of shares of the stock plus some amount of a bond, right? We need to assert some assumptions about the portfolio. So 1B is riskless, right? By riskless, I mean it satisfies the differential equation for exponential growth. So B of t is just e to the RT. All right, that's the first one. Next one is that C of t equals pi of t, right? So this is the mirroring, right? We want the cost of the option, the price of the option, and the portfolio to be the same value. And you're going to dynamically change these two things. So the way we think about this, right, is that if you have $100 and you distribute it among stocks and bonds, and then every future step in time, you just readjust the numbers and you readjust the numbers and you readjust the numbers. What you never do is you never inject more money, right? You only input the initial amount and then you let it self-finance, keyword, right? So we're going to assume that pi is self-financing. All right, mathematically, what does this mean, right? D pi is going to be equal to delta t ds plus b of t rb dt, right? Because it's going to be dB, but dB is that. And then we can insert real quick the fact that we know that price ds is modeled on a stochastic process, so we can just insert that and we can group up terms and we can get the following. And we can get delta t mu s plus phi of t rb dt plus delta t sigma s dw. So we have our portfolio. It satisfies that SDE, and we're claiming again that they're equal to the cost one. So now we just put them together, right? We want to use Ito's lemma on C, right? So that chalk is running out of color. All right, so we have d pi equals dc, but by Ito's lemma, dc is going to be equal to partial v partial t plus partial v partial s mu s plus 1/2 partial v partial s squared sigma squared s squared dt plus partial v partial s sigma s dw. And now you make the magic trick, right? Choose delta t equals partial v partial s, right? And by doing this, phi b is going to be equal to v minus s partial v partial s, right? Because you have an algebraic relation, right, between the pi is equal to c, c is equal to v, and pi is a combination of s and b, right? So what happens if you make this magic trick, right? Well, let's observe some things. First one is that there's a vs sigma s here, and there is a delta sigma s here, dw. They're the same thing. If you make this assumption, these guys cancel, right? So that's the first improvement. Now, if you make the second improvement, right? So if you shove this guy into here, and substitute this guy into there, you get the following expression. So after substituting, this is the last page, guys. We're a little over, and we'll get through it. RB minus. All right, this equation looks quite long, but you'll get the essence in a second. So now what do we notice? Right? So I wrote it all out. I just effectively shoved in this part with the right substitutes, and I set it equal to that thing. And these are both the dt pieces. What do you see? Anyone see it? Barring my handwriting. The parts with the drift are the same. So these actually cancel. That is to say, the problem that we had before was that we're not risk adjusted. Right? The drift causes problems. Drift is mu, right? Doing this cancels the drift out. So this is removal of drift. Right? So by making this clever choice of what delta should be, right? And hence what b should be, or phi b should be, you actually cancel out the drift. And now we get the PDE that it's all named after, right? We rearrange terms, right? And we get partial v partial t plus rs partial v partial s plus 1/2 sigma squared s squared partial v partial s squared minus rv equals 0. And then you have the terminal condition vs of t equals s of t minus k plus. And now this is the derivation of the Black-Scholes equation. And I will say one word of how you actually solve this thing. I won't write anything down, so we're done with writing. So you look at this thing and you say, okay, well, we need to solve for a function v, and then we just plug in t equals 0, and we're done, right? The clever trick that you can make is if without, it's not immediately opposite, but this actually reduces to the heat equation. So if you make like 4 change of variables, this thing will become the heat equation, and you can solve the heat equation by convolution, right? This terminal condition will become a boundary condition in the reduction, and you can solve the heat equation with that boundary condition, right? And what you can then do is reverse the entire process, right? You find what the heat equation is, you rebuild V by undoing all the substitutions you made in a row, and you get a closed formula for V. And so I'm gonna lie, and I'm gonna write that, and we'll call it a day. So at least I can say I gave to you the closed form solution. So V of S and T, after doing all the words I just said with the heat kernel, going to equal to S times V1 D1 minus K e to the minus R big T minus little t B D2, where D1 is ln S over K plus R plus sigma squared over 2 T minus T. Yeah, it's a little bit ugly. You know, this is what happens when you change variables a bunch of times. D2 is not as bad, this is D1 minus a shift. And this guy is the cumulative normal distribution function, so it's the CDF of normal distribution of 0, 1. And it may look ugly, but it's at least a closed form, right? You plug in T equals 0, you plug in the initial stock price, V of T is the price of the call. Sorry for going over actually a non-zero amount of time. All right, thank you everyone. Happy Halloween.
Are there any question for Jason?
Basically, this is the only stochastic PDE you can solve. You can give the closed formula.
Yeah,
This is the only one, really.
so the one thing I didn't get to cover that, I mean, for those who have to leave, of course, you know, you're free to leave. I'm not gonna hold you here, right? This is the price of a call. You can price a put as well. So maybe you say, oh, well, we priced the call by doing this method. Why can't we just price a put? And the answer is, okay, like maybe we can just go through this whole process again and we can price a put. It turns out you don't have to do that. So if you're a put and a call that have the same initial price, strike price, time, then you have the put call parity, which says the price of a call minus the price of a put is K minus e to the minus RT. Oh, S0. There's an S0 minus K. There we go.
Mhm.
So the price of a put can be derived, the fair price of a put can be derived from the fair price of a call by this clever parity argument. So actually we've solved killed 2 birds with 1 stone, right? You solve the call one, you get the put one, and life is good. And once you have calls and puts, then you can build all the spreads your heart desires, right? So, Yeah.
So, I know that this is not like, really, a short answer, but roughly speaking, is there like existence uniqueness, like for PD, do you have like a priori estimate?
For which thing?
For like those kind of like.
this PDE,
No,
like this one in particular, or do you
like-
mean
like-
SDEs more generally?
as the.
Yeah, you have the existence uniqueness theory. So I only made a simple comment about this because I didn't want to spend any time, but yes, you can, there is a similar like ODE type argument where if you have Lipschitz constants or, Lipschitz
Oh.
control over the big function, then you can actually solve.
Oh, Brett.
No, I don't know that. This is the analyst stuff.
No,
sure.
I don't.
But there is an existence uniqueness theory for SDs, or at least ordinary, right? All of this, by the way, is ordinary stochastic differential equations, because it only involves time, right? You could do
Oh.
partial differential equations where you have more than dt, you have your
Wait,
dx, dy, your
is
dz's.
that a PD because it
This thing.
time and.
Yeah, this is a PDE,
Is a PDE.
right? Well, this one you have to be a little bit careful with, because of course, S is a random variable.
Right.
So this equality, again, you have to be a little bit careful with, because this is also, like equal in the L2 sense, right? But you could write down the PDE, like you could just erase the fact that S is a dependency, S of T, and just say that you have a function of R and S, or a function of S and T as, 2 real variables. Solve that PDE, and then just shove in S of T at the end.
Like, do people solely works on like existence uniqueness?
For this, or, well, we can talk about this later as well, like we can have.
I think-
I don't want to hold everyone up.
I think people usually use numerical analysis to solve this.
That's right.
because they care about the solution, they don't really care about.
All right, well, if there's no other questions, thank you for everyone. Oh, yeah, sorry.
In a Black-Scholes equation, in the setting, you have an assumption about the stock price, I mean the PE. Is that reasonable enough in real life?
Well,
course not.
Brandon was screaming at me a little bit ago,
not.
but you have to be careful, right? So there's more things that happen in real life.
They,
Right, this is a simplified model to get, so before this, maybe a historical note, is before these, Black and Scholes wrote this down, there was other models to price options.
I see.
This wasn't the first thing that existed. The problem is that those other ones depended on parameters. This becomes parameter independent. So although it may not be the best model, right? In fact, it won't necessarily model the true day we see. This was the best of its time
I see.
at giving you a realistic chance.
See, so the model changed. Like no.
Yeah, but there's also American.
I think
right? What
nobody
about
really
another
uses
set of
this
options,
anymore, I think no one really using this in industrial. Basically.
All right, I'm not gonna hold you up anymore. Thank you again for coming. Everyone have a nice Friday.
Station.